Today I would like to talk to you what you can or should do when your training data contains misclassified labels or noisy target values, a subject known in the scientific literature as label noise. I decided to talk specifically about this subject since I truly believe it has an impact on various fields and applications in machine learning and deep learning. I hope that by the end of this short talk, at least some of you will find the ideas presented useful for your everyday machine learning research. Just to make sure that everyone understands, I want to stress the difference between two types of noises common in machine learning: attribute noise and label noise. In attribute noise, it means one or more attributes in the training data have wrong, missing, or incomplete values. This may occur to deliberate altering due to measurement errors or data corruption, like the example you see on screen in which the original images were added Gaussian noise in order to model possible blurring of the original image. In general, if the probability of attribute noise is neglected, this might cause the model prediction to become less accurate. But now think of a different situation in which not the attribute, but the original label given to the instance is wrong. This is known as label noise. In general, when comparing the two, researchers have shown that label noise is much more harmful, and as such it is important to understand how to handle it in machine learning models and pipelines. Researchers have shown that label noise can deteriorate the overall performance of machine learning models. This occurs since label noise alters, at least to some extent, the relationship between the measured output and the features. One example for it you see on screen, in which we tested the accuracy of 3 different classifiers: a random forest, an SVM with an RBF kernel, and an SVM with a linear kernel as a function of percent of label noise in the training data. Although they all show a different pattern, all of them show a degradation in their performance as the level of label noise in the training data increases. If you're a bit puzzled why they have a different pattern, don't worry, you will get the answer by the end of this talk. Unfortunately, this is not the only downside of label noise. Researchers have found additional downsides, such as a difficulty in performing feature selection, a substantial increase in the complexity of learned models, and the need to increase the training data in order to produce the same test accuracy. Like the example you see on screen, where the researchers needed many more clean training instances in order to reach a 90% accuracy threshold in case the data was very noisy in comparison to the noise-free baseline. In general, label noise can occur due to several reasons. First of all, expert labels do make mistakes from time to time. The second is categorization of certain instances may be subjective or very confusing. Like I think the people in the back are having a bit of a hard time now differentiating between the chihuahuas and the muffins. Data corruption can occur due to encoding problems or to typing errors. And fourth, which is really relevant to current day machine learning, since labeling is a tedious thing to do, we often search for cheaper alternatives, such as crowdsourcing or image annotations obtained directly from the web. And I think you will agree with me that such data sources might produce labeling of lower quality. If we look at the statistical properties of label noise, we can use the same terminology as in missing values. As such, we can divide label noise into 3 categories. The first is noisy completely at random, in which there is a probability P, which is independent both on the feature space and on the original true label, but the observed label is different from the true label. The second is noisy at random, where the label noise depends solely on the true label, but is still independent of the feature space. This might occur if instances of certain classes are more prone to being misclassified. This allows us to define an asymmetric label noise, and by so we can define a transition matrix in which the ij component depicts the probability of obtaining a class I when in fact the true class was class j. The third type is noisy not at random, where the label noise depends both on the feature space and on the original label. This allows us to model cases in which label noise is more frequent in classification boundaries or more frequent in low-density regions in the feature space. In the same way that we examine classification, we can also examine regression tasks. In general, most of the time we assume that the error is additive and follows a zero-mean Gaussian distribution. But in the same way we did in classification, we can also define other categories, such as noisy at random, where the error depends only on the target value, or noisy not at random, where the error depends both on the target value and on the features. I guess you understand by now that the mission of label noise research is to find algorithms that can help reduce the negative effect of label noise. To do so, researchers need to find ways to make machine learning models and pipelines more robust to different types of label noise. In general, the scientific literature depicts three methods, or three approaches, how to handle label noise: a cleansing approach, a robust model approach, and a noise-tolerant learning approach. In the next few slides, I'm going to briefly describe each of these approaches and give you examples how they are used in machine learning pipelines. The first is the cleansing approach. It is based on detecting instances which are suspected of label noise. Once these instances are detected, you can either filter them out, reweight them, or relabel them based on the label the model thinks is right. The detection of these instances can be done using scoring methods which are also used in anomaly detection or in outlier detection. Like you see this simple example on screen, where I used a nearest neighbor approach in which we filter out instances if the class instance does not agree with the majority class of instances near it in the feature space. Unfortunately, these methods are sometimes unable to differentiate between mislabeled instances or hard to classify instances. And furthermore, they tend to filter out instances for minority classes, which will make the classification even harder than it was before. The second is the robust model approach. It is based on methods which are inherently more robust to label noise. In this situation, even if the model is neither filtered out nor modeled, these models still show high tolerance when trained upon learning sets contaminated by target value noise. In general, this approach is divided into two methods. The first method examines different ML architectures and models' robustness to label noise. Like the example you see on screen, in which the researchers have examined 3 different neural network architectures' robustness to label noise. The second model focuses on the robustness of different loss functions, robustness to label noise, in the context of empirical risk minimization. In this example, you see that the researchers have examined 2 loss functions, a median absolute error and a categorical cross entropy, which were used as loss functions for a multi-classification task done using a convolutional neural network. In the specific example, the researcher has shown that median absolute error is more tolerant to label noise. The third is the noise-tolerant learning approach. It is based on models that learn the model weights and the noise distribution parameters simultaneously, while assuming a certain prior regarding the label noise. In this specific example, we talk about models which can learn the noise parameters simultaneously with the model parameters, like in an example using a Bayesian approach, in which you will assume a certain prior. A different approach is to use a parametric approach. If you can assume that the latent structure of the features is indicative of the true label, you can use both the features and the noisy labels in order to model the true labels. And by so, you use a semi-supervised approach to handle the label noise in the data. I added one example of a machine learning pipeline which incorporates a model prediction and a noise distribution parameters learned simultaneously. In this example, in order to handle the presence of label noise in the data, the researchers have added a noise layer, which is the final layer of the neural network, which depicts the contamination process. If we can assume that the noise follows a noisy at random situation, this layer will be linear by nature. That is, this is a class size by class size matrix depicting the transition between true labels to noisy ones. During the training, the model will learn both the prediction model weights and the noise weights, and after the training we can obtain the true labels by the output of the layer prior to the noise layer. In the rest of this talk, I'm going to showcase two practical examples of using noise handling methodologies in a regression task and a classification task. This example will show you that incorporating such methodologies in a machine learning pipeline help improve the robustness to label noise. These methods are based on two out of the three approaches described earlier in this talk. The first one will be a classification one. It is based on a random noise which was used to contaminate the well-known MNIST database. The contamination process in this example was done solely on the training data, while leaving the test data noise-free. Just to make sure that everyone remembers, MNIST is a database of grayscale images of 100 digits ranging from 0 to 9. In order to solve this multi-classification problem, I used the well-known Linnet network. It consists of two blocks, where each block consists of a convolutional layer and a max pooling layer, where the second max pooling layer is fed into a fully connected layer. In order to handle the presence of label noise in this data, I decided to use a relabeling approach. And as you remember, relabeling is one out of several methods used to clean the training data from suspected noise-contaminated instances. The relabeling is based on an approach suggested by Liu just over a year ago. It is based on the assumption that the neural network can replace labels which are suspected of noise contamination. It is based on the assumption that as the training progresses, the model becomes more and more accurate, and the model predictions can replace the original labels given to the instance. It is also based on the assumption that neural networks can quickly learn a reasonable prediction model before completely fitting to the noisy labels. How is the relabeling done? In each epoch, the model selects for each instance the label O as the max activated neuron, that is the model prediction based on the prediction from the previous epoch or the original label. The model gives the opportunity for the neural network to update each label for each instance in every epoch, and by so hopefully to correct noisy labels in the data. The selection which one will serve as label is based on a Bernoulli distribution with an increasing probability as the training progresses of selecting the max activated neuron, that is the model prediction as label, over the original label. To achieve this effect, the probability of the Bernoulli distribution was selected to follow a decaying exponential function as the number of epochs from the beginning of the training. As such, as CT decreases, the probability of selecting the max activated neuron increases, where if CT equals 1, we only choose the original labels as labels, and if CT equals 0, we only select the max activated neurons as labels. In the next two slides, I'm going to show you the results of this experiment. First of all, I was interested to know what will happen if I change the labels of 40% of the instances from the training data, where the corruption again is done only on the training data, not on the test data. As you can see, the data corruption caused the test accuracy to decrease to just under 60%. However, you also see that in the beginning of the process, the model quickly learned a reasonable prediction model, and as such, after approximately 20 epochs, the test accuracy reached a maximum of about 92%, and also the training accuracy remained relatively low, since the training data consists of only 60% of the instances which were not contaminated by label noise. Afterwards, I reran the optimization process, but now with the relabeling method. As you can see, adding the relabeling increased the task accuracy from 57% up to 93%, meaning the model become much more robust to label noise. As occurs as the training progresses, the model predictions replaced the original labels given to the instance. As you remember, the model predictions were accurate in predicting the non-contaminated instances. The next example will be a regression one. It is based on a project I did 7 months ago while working in Similarweb. The project goal was to estimate the monthly active usage of Android application. That is the number of users, or the percent of users that use the application at least once during the month. This project was challenging due to several reasons. One of them is that our learning set consists of target value noise. In order to handle this ensemble, I decided to use an ensemble regression model in which the initial estimations are based on different regressors that estimate the monthly active usage from my data. The estimation of these regressors serve as features for the ensemble method, thus combining all the estimations into one predictive model. In order to handle the presence of target value noise in the data, I decided to use methodologies from two approaches. A loss function which is suited for target value noise, and a filtering method. The loss function is based on a robust regression method called M-estimation. M-estimators are regressors which are inherently more robust to target value noise or to high residuals, where in the context of target value noise, high residuals are quite indicative of instances contaminated by target value noise. The trick, as you might call it, which makes this robust regressors more robust to target value noise, is that they replace the squared error loss with a different loss function which practically diminishes the effect of instances with high residuals. You can understand how they work using this simple example, in which you see the loss functions of 3 different regressors. 2 are robust regressors, Huber and Tukey, compared to the well-known least square regressor. As you see, the loss function increases less rapidly as a function of the residual in comparison to the loss function of the least square regressor. And as such, the minimization process will be less affected by instances with high residuals, meaning their training will be more tolerant to instances possibly contaminated by target value noise. The filtering method is based on an anomaly criterion suited for a regression task. The anomaly criterion is based on 2 factors. The first is the ratio between the target value and initial estimation of each instance, where again, very high ratios and very low ratios are quite indicative of target value noise. The second is the target value itself, where instances with higher target values have a bigger impact on the estimation. The criterion is based on taking the logarithm of each of these factors, multiplying the 2 of them, and taking the absolute value. The filtering method itself is quite simple. First of all, we use an initial estimation for each instance. Then we can compute the anomaly criterion and filter out the top P% of instances according to their score. Then we retrain the model, but without those instances. And then we can get the final regression model. However, you need to remember that the filtering is done only to the training data, since there is no way to be absolutely sure which instances are in fact contaminated by target value noise. Here you see the results of this experiment. In this experiment, I used 3 different loss functions, which is Huber and Tukey, which are robust regressors, and the squared error, in which every loss function was used once without the filtering method and once without the filtering method. You see the mean absolute relative error scores on the left side of the screen. First of all, what you see is the choice of loss function plays a major role in improving the estimation quality, where robust regressors outperform regular least square error. And second, you see that the filtering method further improves the estimation quality, where there's a bigger impact on the squared error and a small but still positive impact on the robust regressors. You need, of course, to remember this is only one example, and maybe in other example, the filtering method might play a much bigger role in improving the estimation quality. Afterwards, I examined the effect of changing the threshold for the filtering method. In this specific example, the best result was obtained while choosing the threshold to be 0.25, meaning the best result was obtained when filtering 25% of the instances from the training data. You need to look at this as an equivalent process to hyperparameter tuning than in other supervised machine learning tasks. That's pretty much all I wanted to talk to you about today. I want to leave you with 3 take-home messages. First, label noise can do harm for your model if neglected or not treated. The second, I described many techniques and many methods how to handle label noise. What I think you should do is go home, try different approaches, the one which suits the specific application you're working with, and see if it helps make your model more robust to label noise. And the third, there are still a lot of unanswered questions remaining in this field, and it's interesting, at least for me, to try to tackle these kind of problems and find innovative solutions to them. Thank you very, very much for listening, and if you have now any questions, I will be more than glad to answer them. Thank you. Yeah?
How do you mitigate the risk of filtering out examples that your model thinks are mislabeled and they're actually correctly labeled?
Okay, that's the problem of the first approach. Is I told you there is no way to be absolutely sure. And in this second example you saw, I told you I filtered out only instances from the training data. I left all the instances in the test data. In a general case, yes, when you use the filtering method, it might filter out instances which are in effect true, hard to classify. It happens. There's no guarantee that you filter out instances that were actually contaminated by noise and just not very hard, or your features are not good enough to differentiate them between other classes. Any other questions?
For the first problem, the data, it's a binary classification?
No, it's a 10-class classification.
10-class classification. So, you presented the evaluation method was accuracy.
Yeah.
But it doesn't really give the full picture because we don't know what happens in terms of false positives or so. I'm wondering if that's also something that.
What I was interested specifically was the accuracy, how accurate are you in predicting the test data set. And in this example, you saw that I didn't change the labels of the test data. It was a simulated example. In real data, you don't know, but when you think about label noise, you think about the end product, where an actual person sees that and you don't want to tell him, this is 5 and actually this is 7. Yes?
One of your methods, I think the second one or the third one,
okay,
would say that there is a need in some prior knowledge.
Yeah, regarding the noise distribution, yes.
So what is it?
You can think of defining distribution of the noise, if it's correlated to some features, etc. Like if you do it in a regression task, you say it's a Bernoulli distribution or binomial distribution, whatever. Depends on the specific question you're asking. But the example is because you are interested to solve this problem, sometimes you try to solve it in an analytical way, so you need a distribution in order to solve it. Other approaches you can use, I said you assume that the features are indicative of the trip. This is also prior information. You assume that they are actually indicative of the true class. Does it answer your question? If you have any others, I can explain in more detail, of course. Okay, so again, thank you. And these are a list of references if you're interested. There are many more. There are a lot of research in this field, especially in the last couple of years.
Can you, in the site, upload the...
Yeah, it's in the site. You have all the references, and if you write label noise, you will see, let's say, 100 of papers in this field, especially in the last couple of years since deep learning became so common, it made label noise become even more common. So again, thank you. Have a good evening.
Cool.